Welcome, and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session. At that time, if you would like to ask a question, please press star then 1 when prompted. This call is being recorded. If you do have any objections, please disconnect your lines at this time. And I'd like to turn the call over to Ivy Allen. You may begin.
Hello, folks. Thank you for joining us today, and welcome to the webinar on the Colorado River Basin Water Supply and Demand Study. Our presenter today is Ken Nowak. He is a hydraulic engineer with the Boulder Canyon Operations Office of Bureau of Reclamation in the Lower Colorado region. He is stationed in Boulder, Colorado, as part of a planning and modeling team. Ken joined Reclamation while completing his PhD in Water Resources Engineering at the University of Colorado. He was also heavily involved in Reclamation's recently completed Colorado River Basin study, which he'll be presenting on today. Ken, I will go ahead and turn it over to you, and thank you very much for offering this opportunity to us.
All right. Thank you, Ivy. I appreciate the opportunity to be here, and yeah, if you have any questions, please hang on to them until the end, and we'll try and get to them, and hopefully not forget about anything, because there's a lot to go over here, and I'm sure there will be some questions. So let's get right into it. So the objective of the study was to assess water supply and demand imbalances on the Colorado over the next 50 years, and then evaluate and develop opportunities to resolve those imbalances. This study was conducted by Reclamation and the 7 basin states in collaboration with stakeholders throughout the basin. It was a 3-year effort beginning in January of 2010 and completed recently in December of 2012. This was a planning study, so it did not result in any decisions, but it provided more of a technical foundation for addressing these challenges in the future. Now, I'm going to assume that most of you all are pretty familiar with the Colorado, the layout, but to the right we have our basin study figure, our map, and you can see the hydrologic basin is delineated with that heavy black line. What's noteworthy, though, is beyond that heavy black line, there's a number of areas shown in red hatching. Those are adjacent areas that receive Colorado River water. You'll see Southern California, the Front Range of Colorado, et cetera. And in order to complete a study that's consistent with our objective, we really need to consider not just the hydrologic basin, but all the areas that receive Colorado River water to really develop the total potential demand for Colorado River water over the next 50 years. So that's a really important thing to note here as we get going, is we're looking at more than just the hydrologic basin. So to provide an overview of the study and also an overview of what I'm going to talk about here, we had 4 major study phases. There was a water supply assessment, essentially what could the next 50 years look like in terms of water availability in the Colorado Basin. Then there was a water demand assessment. What could the demand for water look like? How could that evolve over the next 50 years? With those 2 complete, we then moved into a system reliability analysis, essentially looking at how the system might perform under those supply and demand combinations, and how could the resources be impacted, and what's the imbalance really, which is the primary objective of the study. And then phase 4 gets into this developing options and strategies. How can we potentially close that gap or work towards resolving those imbalances using the different tools that we may have or could develop. Quickly, I'll just plug that we did have contracted services helping us throughout this study. It was a huge effort that we could not have done alone. DH2M Hill and Black and Beach were pretty much along for the entire...
Ken?
Yes?
I'm sorry, this is Ivy. We're getting a couple questions coming in saying people cannot hear.
Okay.
Allie, is there something we need to do to correct this?
No, everybody is live. Everybody that's in the call is able to hear. Maybe they just joined the net portion and didn't dial in, I'm assuming.
Can we turn audio on the net portion for people that are trying to listen?
I know they would have to dial into the conference call. Yes.
Okay, I will send them that information through the chat, and I apologize for interrupting, Ken.
Not at all, and if it's that they're hearing me but not hearing me well, please let me know, and I'll try and speak up or speak more towards the phone. But if they're not hearing me at all, I don't think there's a whole lot I can do about that right now. All right, so as I was saying, we had contracted services to help us. It was a huge effort, and CH2M Hill and Black and Beach were along essentially for the entire study. And in 2012, we also brought on the RAND Corporation to help us towards the end of the effort, and that worked out well on all fronts for us. I'll plug here just our final study reports. Now that the study is complete, these are all available on our website. There's an executive summary, which is the easiest, most digestible, shortest piece, obviously. That pulls from our study report, which is about 100 pages, and then the study report actually draws from technical reports A through G, and each one of those is another 100 or more pages. So we have over 1,500 pages here. It's pretty hefty, but as I go through this presentation here today, I'm going to try and identify which reports I'm drawing from so that if there is anything of interest, hopefully you can note down which reports you might be interested in getting and continuing to pursue and read. So to start off, we're going to look at the water supply and water demand assessment efforts. This largely draws from technical reports A, B, and C. So one of the biggest challenges in this type of an undertaking is dealing with the uncertainty associated with a 50-year horizon. It's really difficult to know what it's going to look like, and so it's not really useful to try and determine what the most likely future is going to look like. So we employed this scenario planning approach where we tried to identify what a broad, realistic range of plausible futures were and focus our energy on really developing scenarios that span this sort of cone or range of uncertainty, as opposed to using our energy and efforts to try and figure out what we think will actually happen. So it's more of a scenario approach as opposed to trying to really determine what's going to happen. And that allows us to understand how the system might perform under these range of plausible futures, and then that allows us to explore the imbalance and impacts to resources and all the things we're really interested in. So for the water supply scenarios, we had a couple of ways of looking at how the future might unfold. The first was what we called an observed resample. You see the figure here. This is our historic record of stream flow at Lee's Ferry, which is the key location in the basin. What this scenario looks at is what if history was to repeat itself. And so we simply take our historic record and we grab 50-year chunks because we have a 50-year planning horizon, and we just use that as the future. Our next scenario looks for additional variability, and it draws on a lot of the work that's been done in the basin reconstructing stream flow based on tree ring samples, and it's a paleo reconstruction is what it's called. And you can see this record is actually quite long. It goes back about 1,200 years, but we use the same concept of what if the history repeats itself, but now we just have a much longer, more variable record to draw from. Our third water supply scenario is really a hybrid combining the first two. There are strengths on each of them. The strength of the observed record is, well, that we have pretty good confidence in the magnitudes of those stream flows because of our gauging networks and things like that. However, it's a shorter record, which is the strength of the paleo stream flow because it's a much longer record. So what we do in the paleo conditions is we take the variability, the wet-dry sequencing information from the paleo record, and we overlay observed magnitudes on that wet-dry sequencing in order to build a confident but more varied stream flow data set. And so that's our third scenario. And then our fourth scenario is this downscaled GCM projected, essentially climate change if we take output of temperature and precipitation from climate models, and then we use a high-resolution hydrology model to translate that into stream flow. What could the future conditions on the Colorado look like going forward under that type of a scenario? And so we have 4 total water supply scenarios. So quickly, to provide some summary on how this quantification played out, we have box plots here of the average stream flow for the period of 2011 to 2060, which is our study period, and it's at Lee's Ferry. And so what you can see is that the observed resample, their history repeats itself, is the first column, and it's got the highest average flow. When we move to that paleo history repeats itself scenario, the orange one, you can see that that average flow is a little bit lower. When we move to the hybrid paleo condition, you actually see that we do introduce a lot more variability, but the average comes up a little bit more because we're actually using those magnitudes again from back on the blue, the observed history repeats itself scenario. And then finally, if we look at the red, the climate change downscale GCM scenario, we see that the most variability, the widest range of the box and the whiskers, and we also see the lowest average flow. To offer some perspective and sort of ground ourselves that we think that this is a realistic and plausible future, we've plotted here the most recent roughly 20-year average flow from our historic record as that horizontal dashed line. And what you can see is that the 20-year historic average most recently is actually almost dead on with what we're saying the average of that climate projection scenario would be for the next 50 years. And so in our mind, that's a very plausible, still very realistic scenario. It's not something so outlandish that it should be discounted by any means. So changing gears here to the water demand assessment, we developed first narratives describing several ways that future demands could play out, and then we actually quantified putting numbers to those narratives in order to develop the demands that we use in our modeling and the rest of our analysis. There are 6 total, 4 primary narratives, but 2 of them bifurcate, so you get 6. The first current projected is pretty self-explanatory, growth, development, etc., along recent trends. Slow growth is also pretty self-explanatory, looking at growth that is at a slower rate than what we've seen recently. And then rapid growth is sort of a strong economic resurgence, population growth, etc. This is one that bifurcates. The bifurcation has to do with the adoption of technologies with regards to water use and water efficiency. C1 is a slow technology adoption. C2 is a more rapid technology adoption. Last, we have this enhanced environment scenario narrative. Essentially, this is expanded environmental awareness and stewardship coupled with, a growing economy. And the bifurcation here has to do with population growth. D1 was a slower population growth, while D2 was a much more rapid population growth consistent with C1 and C2. So when we put these together, we end up with our demand scenarios, all 6 of them, and they're plotted here. You can see historic use and then our future projections. By 2060, for the basin, the consumptive use ranges from 13.8 to 16.2 million. When we look at including our deliveries to Mexico and also system losses, that jumps up a little higher. But generally, it's about a 20% spread across the high and the low by 2060. If we look at a little bit more detailed view here, we have 3 time slices to look at our demands and how they're growing and changing relative to each other. You can look at it basin-wide, you can look at it by state or by upper and lower basins. But generally, the driving factors here are population, per capita water use, and irrigated acreage. I mean, there's a lot of other factors in here, but those are kind of the big ones given that agriculture and M&I water use are such a big portion of the overall demand. Population is about 40 million currently being served by the Colorado, and that grows to 49 million in our sort of lowest growth scenario and as high as 77 million in the more rapid growth scenario. Across all of these different demand scenarios, water use per capita is decreasing anywhere from 7% to 19% by 2060. And while not the case for every scenario, if we average across the 6 scenarios, we did see a decrease in irrigated acreage of about 6 to maybe 15%, depending on which one you're looking at, and of course the region and things like that. But those are the major drivers, and that's what's kind of behind our water demand quantification. So when we couple them together, we get this figure here, which starts to illuminate what the imbalance could be. You've got historic water supply and water use sort of left of that vertical dotted line, and then our projections to the right of it. You can see that the demand's pretty much surpassing supply in just about all the scenarios when you get out towards the end of our horizon. And if you squint and you kind of look at the middle, it's about 3.2 million average imbalance. It's really tough to develop something like this, but there's a substantial difference between demand and supply. And obviously this can be more or less depending on which supply scenario and demand scenario you pick. And then last, I'll just note, if you're looking at the historic data, you can actually see that supply or demand has outpaced supply in some years, and we've been able to make up that difference through stored water. However, this isn't a long-term sustainable solution to the imbalance. It's only a occasional year-in, year-out drought type of response. Okay, so what I'd like to do here is move on to the system reliability analysis. This draws from technical reports D and G, and this is going to focus for now without options and strategies. So what this means is, what if the system evolved over the next 50 years under these different supply and demand scenarios, and we just sort of let the institutions that are continue and didn't try and do anything to resolve these imbalances? So what we have here is our map of the basin, but now you can see it's got all these dots on it. And what we did is we developed metrics for our 6 resources across the basin in order to allow us to monitor them through our modeling efforts. We're simulating the system over the next 50 years, looking at all these different supply and demand combinations. Eventually, we'll do it with and without options so that we can see what's our baseline without options, and then when we start implementing these options and strategies to resolve the imbalance, how do things change? The resource categories generally are water deliveries, electric power, water quality, flood control, recreation, and ecological. And you can see they're throughout the basin and pretty pervasive. We actually have about 90 metrics across all those 6 resource categories. So in order to do this type of analysis, we use our long-term planning model. It's called the Colorado River Simulation System. It's implemented in the Riverware River Reservoir Modeling software package. As it's a long-term planning model across the basin, it simulates operation at the 12 major reservoirs and delivers water to over 500 water users, as we call them, and it's a monthly model. The model has rules and logic that reflect reservoir operations, sort of an if-then type logic to mimic what actually happens in the river, and allows us to look at a range of potential future system conditions associated with those different supply and demand scenarios. Okay, so what we have here is a schematic that looks at our system reliability analysis approach. The baseline here is defined by generally 3 dimensions. You've got supply scenarios, and as we discussed earlier, there's 4 supply scenarios. And as each one of those includes a number of individual traces or realizations, we have a total of about 2,000 ways to look at the next 50 years from a hydrology perspective. We then couple those with our 6 demand scenarios, and then we actually have 2 assumptions about how the major reservoirs would be operated going forward. And so all of that gets fed into our model, and that provides about 23,500 traces or realizations of the next 50 years. So already we're generating a lot of data. And on each one of those individual traces, we're monitoring 90 resource metrics across those 6 resource categories. So very quickly you're getting a lot of data, a lot of results. And so what we determined was it would be helpful to reduce the number of metrics down a little bit in order for presentation and sort of digestibility. So we developed this idea of an indicator metric, which sort of summarizes a number of metrics within a resource category and makes things a little easier. We also identified this concept of vulnerability, meaning as an indicator metric is performing, can we apply a threshold that really identifies this is when this metric has been degraded so much that we're really seeing the resource being negatively impacted beyond which we'd like to see. And so that was a process that we had to engage different stakeholders and different experts to kind of develop those. But ultimately, we end up with resource vulnerability for the 26 different indicator metrics. Now, we do have results in our study for all those 90 individual metrics, but they're just not easy to present because there's so many of them and the data is so big. So they're in the results and reports, but I'm not going to show them in this presentation today. So if we start looking at results, this is, again, without options. This is just looking at our baseline. This figure shows one of our indicator metrics, Lake Mead pool elevation falling below 1,000 feet, which is that water supply delivery resource category. Along the x-axis, what we're showing is the different hydrology scenarios, and then there are 3 different time windows we're looking at. The symbols show the different demand scenarios, and then the color actually shows which of the reservoir operational assumptions are you looking at. And then ultimately what's being displayed here is percent of traces vulnerable. So of the traces that fall under these different categories of supply, demand, policy, what percent of them for that time slice actually incurred this undesirable, vulnerable event? And we can look at that based on all these different dimensions. And what you see is that for each of the 3 time slices, the downscale GCM, which is, again, that climate change hydrology, is the one that's really having the most number of vulnerable traces, the vulnerable events. And it's sort of the primary driver of vulnerability. But as we move through time and look at that 2041 to 2060 period, that third window, we can see that, for example, under the observed resampled, depending on which operational policy and which demand scenario you select, you can have 0 traces vulnerable or up to 50% of traces vulnerable. And so even though hydrology is oftentimes the major driver of these things, the other elements that comprise a scenario are not irrelevant and shouldn't be neglected. And so we developed this type of figure for all 26 of these indicator metrics relative to their vulnerability thresholds. But again, that would involve showing you 26 different slides to kind of get through this. And so we had to make yet another simplifying assumption just to kind of provide a first cut for digestibility. And so what we did was we actually combined the different supply, demand, and policy scenarios together into one pool. And then we could just look at percent of traces that were vulnerable out of all the traces we looked at. And so what I'm showing here now are ecological resource indicator metrics. There's 5 of them. And the only addition now is we have 2 ways of looking at vulnerability. We have percent of traces vulnerable, which is what we just looked at. So it doesn't matter if the trace had 1 year that was vulnerable or all years were vulnerable. It gets flagged the same for this reporting. But then if we look over at percent of vulnerable years, that's sort of the complementary way to view this data and these results, because it allows us to see how persistent was that vulnerability. Were most of the years vulnerable, or did they tend to be vulnerable once and then not be vulnerable? And so the sort of things you're looking for is, do we have a high percent of traces but a low percent of years? That would mean that you should anticipate this event to happen at least once, during these time periods in the absence of any action, but it probably isn't going to occur year in, year out. It might be a once or twice and then kind of not expect to see it again. And so this is one of the ways that we attempted to present a lot of complicated results in a slightly more digestible and easy to look at view. Obviously, if you want to dive into more detail, you can go back to that previous figure that I was just showing, and that allows you to slice things and look at, okay, where are these vulnerabilities coming from? Is it the hydrology? Is it demand? Or is it some other factor? This is the same type of results as we just saw. Now we're looking at some of our recreational indicator metrics and their vulnerabilities. This has to do with river boating, whitewater rafting, and other activities. And we developed indicator metrics for the 3 major upper basin, sub-basins, and then defined thresholds for vulnerability based on the results we were looking at. The thing to note in looking at these results and also previously with the ecological results is that as you move through those time periods, both for percent of traces that incurred vulnerability, but also percent of years, you're seeing those numbers increase, and you're moving more from the green, which is the fewer events, to the orange and the red, which is a lot of events. And so through time, associated with the increasing supply and demand imbalance, you're seeing not just water delivery resources being degraded, but recreational, ecological, all the other resources that are important to the basin as well. Okay, so now that we've identified results without options and strategies, we start to look for ways to improve the results, to build resiliency, and really get those number of vulnerabilities down to a much lower level if possible. And so this is this development of options and strategies, and this is largely Technical Report F. So from the period November 2011 to February 2012, we had a public open solicitation for options to help resolve the supply and demand imbalance as we quantified it. We got about 150 different submissions, and generally they fell into one of 4 categories: increased supply, reduced demand, modify operations, or sort of a government's implementation policy type of realm. You can see here from our pie chart that increased supply was the biggest of the number of submissions we received, but we also got quite a few for those other categories as well. The next step and challenge really was organizing and characterizing these options, trying to group options together that were similar, sort of put them all on a level, equal playing field, looking at things like how much yield could it produce, what is the timing for implementation, feasibility, energy needs, permitting costs, and kind of put these together, and in some cases develop kind of a representative option that spans a number of submitted options. Sometimes it just involved leveling the playing field when you got varying information, but also just developing these criteria characterizing each one in a consistent manner. Out of that characterization effort, we get this sort of measly looking chart, and you really shouldn't hope to read it, but the idea here is that we have several major categories: technical, environmental, social, and other, that each option was characterized based on and rated on an A through E scale, A being a high score, very good, E being the worst score possible. What it allows you to do is look through your options and compare and contrast them, and ultimately help you develop a strategy. So perhaps you're interested in a highly reliable strategy, or perhaps a low energy need strategy for resolving the imbalance. This allows you to put that strategy into place by developing a filter, and then you can look at what options meet your criteria. And that's what really this portfolio development slide is speaking to here. You can see our cartoon sort of showing the pie chart, incorporating different options together to close that supply and demand imbalance. And the idea is that you take a strategy and translate it into some sort of a criteria filter, and then only incorporate the options into your portfolio that meet those filters. And so in that sort of vein, we developed 4 portfolios to demonstrate how options could be used and combined in order to resolve these supply and demand imbalances on the Colorado. So as a summary here, we've got our sort of Venn diagram. The black line is a sort of universe of options considered, everything we got. And so we did a cursory sort of filtering of that to get to Portfolio A. Portfolio A was pretty much everything that was realistic. Maybe some options got dropped out because they just weren't going to be available for our study horizon time period. Maybe they just weren't practicable for whatever reason. But generally, portfolio A is sort of let's take everything and look at this highly inclusive portfolio. Then we applied a few filters. Portfolio B was focusing on options that scored high on technical feasibility and were also relatively easy in terms of permitting and policy risks. And so that created a subcategory or a subgrouping of all the options in Portfolio A. Portfolio C was a different subgroup, essentially looking at low environmental impacts using energy needs and other things as the characterization criteria. And then Portfolio D was sort of the safe bets, things that were common to A, B, and C, and sort of combining all those filters. And this considers the smallest set of options. And so that's important to note because the total amount of yield that each one of these portfolios could offer is different. And so when you sort of go with the common ground, the low-hanging fruit, you're not going to have nearly as many tools at hand to address these challenges. So what we have here is our system reliability analysis, now looking at these options and strategies, modeling these portfolios, and this is largely drawing from Technical Report G. So again, we start with our long-term planning model, CRSS, and we input information about these portfolios and the options that comprise them. Things like timing, when is this going to be available, how much water could it either produce or save, and cost. And so we actually modeled these portfolios in a dynamic sense, meaning that portfolios were implemented using options based on a cost-effectiveness ranking, but only when they were needed. We developed this idea of a signpost where we would hopefully spring into action before reaching vulnerability, but also avoiding implementing options and investing in projects and things when they're not needed. And so the idea was we looked at when these vulnerabilities occurred, what are the conditions that are associated with them, and then we tried to look for precursors, and that becomes a signpost. So we look for the signpost. When the signpost occurs, the model then knows to look into the options that comprise the portfolio and then select of the available options the most cost-effective that will help address that issue, and then continue the simulation. And so we did this process of looking at all four portfolios against all of our different scenarios. So essentially we took that 23,000 traces and multiplied it by 4 here, which just expanded our results in analysis even more so. I apologize here. This is, again, another challenging figure to read in a PowerPoint presentation, but what it's showing here is of all the options that were available and looking at the 4 different portfolios, first, when was that option available to be implemented, and then how frequently did it tend to get implemented? And so the vertical black line represents when that option was available, and then the color bar, the heat map, sort of shows how frequently was it implemented. Green means very infrequently implemented, and then as you get to yellow and then red, it means increasing frequency of implementation. You'll see some portfolios are blank for some options, meaning that option didn't meet the criteria that filtered for that portfolio. And what this allows you to do is to start looking at, okay, how are these different portfolios closing that supply and demand imbalance? Where are their differences and where are their similarities? What are the projects that seem popular across all portfolios? What are the ones that just don't seem to be getting used very much? All right, so now let's actually look at a little bit of results from this supply-demand portfolio modeling, the system reliability analysis, now that we have options in place. What's being shown here is cost, and it's in 2060 in billions of dollars, so it's pretty big money here, but mostly it's just for comparison purposes. And we're looking at percent of years vulnerable in the first column for a key upper basin metric, and in the second column for a key lower basin metric. And so what we're seeing here is of all the water supply scenarios that are out there, all the different 4 that I talked about, what was the vulnerability under the baseline, meaning with no options? And you can see that for the upper basin, it was about 6%, and then for the lower basin, it was about 19%. And then once you start implementing the 4 portfolios, that comes down quite a bit, and it gets pretty close to 0. You'll see that the costs are all pretty similar as well, and what this should indicate is that these portfolios are all drawing from the same common, least expensive, low-hanging fruit, and so there's not a lot of difference between the performance and then also the cost. They're very similar. They're grouped together. Now, if we take that to an extreme and look at the observed resampled hydrology only, which was, if I can use this term, the most rosy, the most optimistic in terms of water availability, you can see that for that upper basin metric, the baseline had no vulnerability, and for that lower basin metric, about 7% vulnerable. So really not a lot of vulnerability to begin with, and you can see that, of course, the portfolios are even more tightly grouped together in terms of A, their effectiveness at reducing vulnerability, but B, their cost. There's not a lot of differences when there's not a lot of work to be done. So let's start looking at the more challenging hydrology. Now I've got just the downscale GCM, the climate change hydrology. And you can see that under the baseline, you have 18% vulnerable, and then under the lower basin metric, you had 44% vulnerable. And then you start to see some separation in terms of the effectiveness of the different portfolios at actually bringing that number of years vulnerable down, but also some differences in terms of cost. And so if you look at the upper basin reliability metric and you look at the effectiveness of the different portfolios, the lowest cost one is that portfolio D, the sort of yellowish colored one, but it's also the least effective. And so you start to see the trade-offs of as I invest more, I'm reducing my vulnerability more, and you can start to understand how the different portfolios are accomplishing that, and if there are any trade-offs to be explored. But to make this the most interesting, what we did was we looked at the lowest stream flow conditions. Essentially, we just took all of our different hydrology scenarios, sort of ignored which group they came from of the 4, and picked the sort of lowest 20% in terms of average flow to kind of analyze, what do these worst case traces look like in terms of how the different portfolios perform. And we really start to see some interesting things here. Again, if we look at the first column, which is the upper basin reliability, we can see that portfolio D is the least expensive, but also does the least in terms of bringing down vulnerability. That's because it has the fewest options at hand to deal with these most dire traces. What starts to get interesting is that if you look at the most effective portfolios, you've got A and C showing about 5% vulnerable, down from 30%, so a significant reduction, but portfolio C is sitting around 5 billion, whereas portfolio A is sitting around 7 billion. So that should suggest that these two are equally effective, but perhaps doing it via different options, which may have cost or reliability or other trade-offs that might be interesting to further explore. Now, the same thing is true for that lower basin reliability metric, the second column. You see that portfolio D is, again, the lowest cost, but really it's doing about the same job as portfolio C is. So there's a trade-off there. And then similarly, portfolio B and A are both bringing vulnerability down into about the 10% range from 70%, which is really a significant improvement, but again at different costs. And so this type of analysis allows us to start asking the questions of what are the common low-hanging fruit, but then when push comes to shove in these really challenging hydrology, how are the different portfolios performing, and what are the decisions that might want to be considered? All right, so what I'd like to talk about now is just a little bit of study limitations and then next steps. The detail and the analysis that we performed in this study was obviously limited based on availability of data, the methods, and also capacity of our models. hoping to further improve in the future, we recognize that these limitations include assessing impacts to basin resources. We looked at these 6 different resources. They're all very different and tried to do it using the same model. A lot of times, each of those resource categories would have its own individual model that really is best at addressing and understanding the impacts to those resources. Obviously, there was a lot of uncertainty in terms of how those options were characterized and how they were scored on those criteria, and then also the consideration of options. And then last, the treatment of lower basin tributaries. The inflow below Lee's Ferry, they're not completely naturalized stream flow, which is what we like to work with, and so we're working to remedy and improve upon those data sets and hopefully enhance our modeling capabilities. But now, perhaps most interestingly, is what are the next steps? Well, this study, in our mind, has really been a call to action. We've identified that there's the potential for significant imbalances and that without action, we're going to see a lot of impacts, negative impacts, on resources beyond just water delivery. I mean, water delivery is extremely important, but it's not just water delivery. So many different organizations and interest groups have a stake in this, and so we really wanted to use this as a springboard to move forward and continue this collaboration that we really saw during the study. So to that end, we have this schematic here that sort of outlines the processes that are going to be going forward that are going on right now. There's a number of multi-stakeholder efforts which are shown in yellow. Primarily, there's 3 work groups that have been established as part of this phase 1. One looking at M&I conservation, one looking at agricultural conservation, and another one looking at healthy flows. And then there's a number of efforts that are going under state direction. They've been looking at these things, they're continuing to look at them: water banking, augmentation, and watershed management. And then reclamation is also doing some efforts, continuing our climate research, working with our tribal stakeholders to better study the system with regards to their needs. And so there's a lot of efforts going on in parallel, but all being coordinated and sort of kept in touch and aware of each other through this coordination team, which is sort of a multi-stakeholder group of folks that kind of keep aware of everything that's going on. And so phase 1 with regards to these 3 work groups that I just spoke of is underway, and we're anticipating some products by the end of this year, and then that's going to inform what we're calling phase 2, which will be taking this the next step after phase 1, and they're going to inform and also recommend what that phase 2 should really look like. All right, so with that, I'd like to just wrap up and thank you for the opportunity to share the work we did on the basin study. Obviously, there's a tremendous amount of information in this study. The results are hundreds of pages long, depending on what you'd like to look at. And so I'm happy to take questions about anything in particular. If you really do want to chew on a lot of results, please go to our website, download the PDFs, look at the results. There's a lot of really interesting information in there, a lot of really good analysis that we did that I think is worthwhile and is really going to take the types of planning efforts that we're working on now into the next level in terms of science and strategies and approaches. So it's a considerable effort, and the report is huge, but there's a lot of good information in there. And if anyone has questions about where to look for something, or is this in your study because the scope is so big, I'm happy to help with that as well. So I guess at this point, I will open up for questions. Ivy?
Thank you, Ken. To ask a question, you just need to press *1, and Allie will open your line so that you can talk.
That is correct. To ask a question, please press *, then 1. You'll be prompted to record your first and your last name so I may introduce you. That's *1. One moment, please. I do show a question coming in. One moment. The question comes from Emily. Your line is open.
Hi, and thank you for this presentation. I am from the Audubon Society, and I was wondering, are there any opportunities for new groups to come in and our new stakeholders for future involvement, and what would be the process for that?
Certainly, we're always looking for additional involvement and perspectives on such a huge, complex system. The best way to get involved, at least being aware of our activities, is if you go to our website, we have an email server list that sends out information about the next steps that I just spoke of in the efforts, and that's really the first step, I guess, in terms of becoming readily and regularly aware of how this is moving forward. If you want to become involved beyond that, you can contact myself, or there's actually a study coordinator who's at our website. Her information is available there, and she could sort of direct you into the correct avenue of how to get involved further.
Great, thank you.
Once again, to ask your question, it's star, then 1. One moment. And I show no further questions at this time.
If we don't have any further questions, we will wrap up. Just if you would like to ask a question, please go ahead and press star 1, and if not, we will close out the call. Ken, I really appreciate the wonderful presentation you gave for us. Kevin Johnson is the coordinator for the Southern Rockies LCC and John Rice. Would either of you like to say anything?
Yeah, Ken, this is Kevin, and again, I appreciate you taking the time to give this presentation. And one of the things I guess I do have a question, and that is that you showed a slide of limitations. Has there been an assessment of what is needed to overcome those limitations to refine the results of this study?
The short answer is yes. In some of those areas, it's a little bit more of a known. Like for example, with regards to the lower basin tributaries, we know that it's not a completely naturalized stream flow record we're working with, and so we have an effort underway to rectify that and improve our capability. It just wasn't going to be available, for the study. Some of the other ones are much more challenging. For example, our model is primarily a water management, water delivery type infrastructure, and so assessing such a varied resource category set can become challenging at times, particularly with regards to something like ecological requirements, which are oftentimes at the daily time step when you have a monthly model. We do have efforts working with various groups like the Nature Conservancy and other stakeholders that have been involved in the study to really improve that, but it certainly is much more of a challenge. It's not nearly as easy to just pin down as we need to do this and that'll really improve things,
Mm-hmm. And then you also had a slide that showed the 3 stakeholder work groups, and I was wondering if you could expand a little bit on what the work group Healthy Flows is focusing on.
I will do my best. I am not actually actively involved with that group, so I could certainly provide you with some more information offline, but generally it's looking at opportunities for not just identifying what healthy flows are, but how to achieve them perhaps, and there's a multi-stakeholder group kind of spearheading that involved let's see, it's folks from the states, the NGO community, as well as reclamation, and they're working to move forward our efforts from the study. And I think the best thing for me to do would be to provide some of the information that I can send offline, because I'm not super tuned in on them.
Yeah, I'd be interested in I guess maybe getting in contact with someone on that work group. So if you could send that, I'd appreciate that. Thank you.
Yeah. The other thing I'll just note for those folks still on the line is our website URL is kind of long, but if you just search Colorado River Basin Study, it's the first thing that shows up.
Thank you very much, Ken.
Of course, my pleasure. And again, if anyone thinks of anything afterwards, feel free to shoot me an email and I can answer your questions or point you in the right direction.
All right, thank you all. Allie, I think we are ready to shut down the call, and I appreciate everyone for joining in today.
That concludes today's conference call. Thank you for your participation. You may disconnect your lines at this time.